So I'm going to talk about mortality, specifically tree mortality, at the density management study. And I'll kind of take a focus on both the rates of mortality that you get with and without thinning. And then I'll also talk some about snag recruitment and what that looks like at these sites. So my specific talking points are, I'm going to ask the question, how many trees are dying and which trees are dying, and does thinning have an effect on this? And then I'll take a little bit more of a specific look at gaps, and there's some concern about gaps increasing susceptibility to wind throw or things like that. So I'll look and see if we have evidence for that in the density management study. And then I'll kind of change gears a little bit and talk about snags and late successional forests and how those compare with what we see at the DMS sites. And then I hope to present some evidence that it may be a wise idea to create some snags. And then one of the issues with that is how long these snags are going to last. So then for continuous habitat. So then I'll also take a little look at that. So first of all, here's the overall mortality rates. On the x-axis, we have the different treatments. I think we've covered these a bit, but they're defined over here again. And on the y-axis, there's an annual mortality. And what you can see is that in general, thinning decreases mortality. This is just overall all trees, all species. And it's only significantly different and lower in the variable density, but there's a general trend of decreased mortality. And I'll point out that the control is a little bit over 2%. So the biggest thing here, and in this graph, there's the DBH size class and 10 centimeter size classes on the x-axis, and the number of dying trees per hectare on the y-axis. And the biggest thing I'd like to point out here is that the smaller Doug firs, this black bar is the control, and these other 3 bars are the different thinning treatments. And what you can see is that there are a lot of smaller Douglas firs in the 10 or the 5 to 35 centimeter diameter at breast height Douglas firs are dying in the control treatment, these black bars. And this is greatly reduced by thinning. But I will point out that the larger trees, and we typically think of large snags as being over 20 inches or 50 centimeters or so, these are not strongly affected by thinning in any of the thinning treatments, and they have much lower mortality rates in general across all the different treatments. And I'll also point out that there's very few large hardwoods. So this is a similar story. This is from the rethin. Those other data were from the initial thin 7 sites, and this rethin is on 4 sites here in Western Oregon. And it's a similar story, but taking a little bit of different analytical approach. In this case, we have the initial size of the tree on the x-axis, and in this case, it's a continuous function. And the probability of mortality over 10 years, so from 1 to 11 years after the thinning treatments were applied. And these stands were either thinned once or thinned twice. And you can see, and this is for Douglas fir, which was the dominant tree species on these sites. You can see that there is a higher predicted chance of mortality for the smaller Douglas firs. And once again, when you get into the larger trees, there's very little effect of thinning, and there are very few that are actually dying over this period of 10 years. So now I'm going to talk a little bit about the gaps and whether they appear to have an effect on mortality rates. And this is a Google Earth image of Green Peak, which is where the field trip will be on Thursday. And you can see these are the gaps. There are a mixture of 1/4 acre, 1/2 acre, and 1 acre gaps. And to try to get at whether gaps have some kind of effect on mortality, I looked at the moderate density and variable density treatments, which have both gaps, leaf islands, and the thin matrix. And what you can see, and you have those 3 classes here, and annual mortality rates on the y-axis. And what you can see is that in general, the leaf islands have almost a 2% mortality rate, which was very similar to what we found in the control. And the gaps are kind of intermediate between the thinned matrix and the leave islands or the control. And so there's no real strong evidence that gaps are increasing mortality. And another way to think about that is to look at the trees directly on the edges of the gaps. And there were 220 of those trees. The plots were randomly placed within the treatment units, so some of them included gaps and gap edges. And 21 of the 220 trees directly on gap edges died during 5 years of this study. And that's just under 2% annual mortality, which again is slightly lower than the control, and in this case very similar to the leave islands. So with all the small trees dying, you may suspect this is due to suppression or competition. So I took a quick look about whether on an individual plot basis in the control, if mortality rates were strongly related to the tree densities. And I'm showing here on the x-axis the initial number of trees per acre, but this is actually the strongest relationship, and it's still not very strong. But I also looked at basal area and things like relative density and stand density index. And you can see 5-year mortality is on the y-axis. And these are the individual control plots and their rates of mortality over 5 years. And a couple things I'll point out is that the rates of mortality on individual control plots are quite variable, and so are the initial tree densities. And there is somewhat of a positive relationship between initial density and mortality rates, but there's still a lot of unexplained variation as well. And this is my but slide. So this is where I point out some of the potential issues. And one thing is we do have a very short data set here with the initial the 7 sites that I presented most of this data from. We're only looking at 5 years. So we're taking a very small time slice. And in particular, that's from 6 years to 11 years after the thinning took place, looking at this mortality. And there are other studies that would suggest that mortality may be higher immediately after thinning, and mortality, especially of larger trees, may be episodic, that comes along with windstorms or snow and those kind of damages. So you could expect if you create a gap or do a heavy thinning and then get a 100-year wind event right after that, you may get different results than what we found at the DMS study sites, or if you're on the edge of a clear cut and do a thinning. Now I'm going to transition a bit and talk about snags, and particularly snags as habitat. And large snags, particularly those over 50 centimeters or 20 inches, make especially good habitat for a variety of organisms. And one thing is that younger stands, such as those in the density management study, often have a variety of smaller snags, but they can often lack these larger snags. And this is a graph from an older paper that shows that as forest age increases, the average size of the snags also increases. And some previous studies have found that we can have from 4 to 17 large snags per hectare in forests of this region. And this is looking at the initial sampling on the DMS sites. And this is the snags that were there on the first visit. And again, we have 10 centimeter size classes, diameter classes on the x-axis, and the number of snags per hectare on the y-axis. And what I'll point out is that those larger snags, such as those above 50 centimeters or 20 inches, there are very few of them, but there are a lot of small snags, especially in the control. Of course, there may be other effects, such as ecoregion or slope or aspect, that are important for determining snags. And this is some recent work by Adrian Aries. And what he found was that, in general, the Coast Range had more snags than the Willamette Valley foothills, and that north aspects had more snags than south aspects. And you can see, in this case, the diameter size classes are again on the x-axis, and it kind of starts with some of the larger snags than what we have on the DMS sites at this point. Now, for the DMS, this is a scatter plot of the 5-year mortality on the y-axis of individual plots, and I've coded it here by treatment. And then there's the folded aspect with the southwest maximum on the x-axis. And what you can see is that so far at the DMS sites, we're not seeing a strong effect of aspect on mortality rates. And the other thing I would point out is that there's high variability among all the treatments for individual plots as far as in terms of mortality. And now transitioning once again to think about, it seems that there are not as many large snags as you might expect in late successional forests of the region. And it's part of the study plan to potentially create snags if they're not being created within 10 years. And so I was going to talk a little bit about how, if you're going to create snags, how long they might stand and then therefore be habitat, and potentially thinking about things like having continuous snags and continuous habitat throughout over time, at least somewhere on the landscape. And this is a graph with trees that were trees that were topped, and this is years after topping, and this is the percent that remain standing. So you can see kind of a logistic function here where the trees kind of fall quickly in the middle, and then some of them stand for a long time. Of course, it probably matters exactly how large these trees are to where they'll stand. And this is a study that took place after wildfire in the eastern Cascades and Blue Mountains. And this is from a chronosequence of about 68 wildfires. And in this case, the probability of a tree standing without a broken top, or standing and having a broken top, or fallen. In this case, fallen is defined as being under 2 meters tall. And I have highlighted here Douglas fir, which is in this middle row. And what you can see is that the general trend is that the larger Douglas firs, so those that are 60 centimeters, tend to stand a lot longer than the smaller snags. So they'll provide habitat potentially as snags for a longer period of time. So in conclusion, generally the small trees, especially the Douglas fir, have the highest rates of mortality, and that's true in the control. And generally the thinning reduces that rate of mortality, and that's true for pretty much all of the different levels of thinning that we evaluated in the density management study. And it does not seem that gaps appear to greatly increase mortality, at least not over the period of this study and under these conditions. And there are a few large snags, greater than 50 centimeters diameter, that are present at the time of study initiation or that are being created through mortality. And so snag creation could be used to supplement the large snags. Okay, thank you.
You focused a lot on the rate of mortality, but another part of the equation that seemed to be missing was the number of stems that remain for mortality to act upon. You know, 5% of 200 trees per acre, you're going to have a lot different number of snags than 5% of 50 trees per acre. So I wonder if you'd look into that question. You know, when Mark Harmon was talking about carbon in a stand, he said that the total growth is a function of individual growth plus the number of remaining. And I think there's a corollary with snags. The total number of snags you're going to recruit in a stand is a function of the size of the snags and the number of stems of live trees that you can recruit from that pool.
Yeah, and that's part of the point. Let me go back a little bit, or to the beginning pretty much. In that the mortality rates weren't greatly different between the control and the thinning treatments. But yes, the number of trees remaining is pretty much directly proportional to how much was thinned. The control has far more trees remaining than the high density retention, which has far more trees than the moderate density, so on and so forth. And so you get a lot more mortality because even though the mortality rates are not that much accelerated, because you have a lot more of these particularly small trees in the control, you do get a lot more mortality in those. So yes, there are a lot more of these trees remaining in the control, especially the smaller trees. And they're dying at a much higher rate. Yeah, and I guess for the larger trees, there's very little difference in rate or the actual number of snags being created, as you can see here. I'm not sure if that totally answers your question, but maybe you got part of it.